Max Welling. I am currently a Vice President of Technologies at Qualcomm, and I am also a full professor at the University of Amsterdam. So my job at Qualcomm is to lead the AI strategy for the company. And at the University of Amsterdam, I lead a research lab. Well, actually, there's a very broad spectrum of topics that we study, mostly around deep learning these days, but also causality is a big topic, reinforcement learning is a big topic, and sometimes with applications in, for instance, medical imaging. Yeah, so what excites me most is to work on new problems, new directions in machine learning, and connect them to sort of real-world applications. So within Qualcomm, this is our bread and butter. But I like to think of problems and abstract them into sort of mathematical problems or machine learning problems, and then work on these abstracted problems. So let's say to map a problem, for instance, in the design of chips, back to maybe an optimization problem that can be tackled with reinforcement learning. And so there's many more of these. For instance, we are working there also, not necessarily me, but in Qualcomm, we're also working on source compression, and sort of we do that using variational autoencoders with which I've been involved. We work on compilation problems, and you can map those, for instance, to graph neural nets. So I like to work on this interface, but also I like to work on completely novel directions within the field, which do not necessarily have immediate applications. For instance, the thing that I'm very excited about now has to do with quantum computing. So is there a possibility to apply sort of the mathematics of quantum mechanics and quantum computers to the benefit of deep learning and machine learning? That is of course a widely open field, and quantum computers are not yet sort of fully developed, and so that this field holds a lot of promise. And then also connecting that, for instance, to the symmetries. If we worked a lot on symmetries, the world is full of symmetries, and this can put structure into your neural networks. That's very beneficial for learning. And in some sense, what's happening is that ideas from physics, which are often mathematics, very deep ideas from physics and mathematics, are finding their way slowly into sort of machine learning. And it's kind of interesting in two ways. First of all, I think these ideas will help make our machine learning algorithms better and more principled in the future. But also we might maybe learn something about sort of physics in some way. At least for me, it's interesting that I can learn more about physics by studying these ideas in the context of deep learning. Yeah, I think human-centric AI is actually very important. But what sometimes confuses the discussion, in my opinion, is that AI and machine learning are extremely broad topics. So machine learning is a subset of AI. So AI, is a very, very large container term for all sorts of things. And sometimes when some people talk about AI or machine learning, they talk about things where explainability and human-centric are less applicable. And then when other people talk about these concepts, they are extremely important. And I don't think necessarily that everybody understands that there is this very broad spectrum of machine learning, and everybody talks about their own view of the world. So let me give an example to make this clear. So think a bank that needs to decide on who will receive a loan. And so this is clearly a decision about people. And there it is extremely important that these decisions are made in a responsible way, in a fair way. And so there I feel that these, regulation and and this human-centric design is extremely important. However, there's also many applications, and actually many of those you find in Qualcomm, where it is much less interesting and important to think about these things. So for instance, imagine I have a black box that will predict, and I have no idea how it does it, but it will predict for me the best design of a chip, right? So I ask it to design the chip with these specs, and it will provide for me the perfect layout of all the transistors and all the memory elements in a way that optimizes, our metrics. Now I can check that it is a really good design, and basically I can just accept that it is a good thing, and I can just build it and then done with it. Now that to me is and there's many of these examples. Compilers are very similar, source compression is very similar, but they're quite far away from the humans that actually use them, and you can very easily check whether they are good designs or not so good designs, right? And I think so we need to really make this distinction when we talk about the importance of responsible AI, and we have to sort of first try to classify what particular AI we are talking about, and then we have to develop methods that will for every class that will be appropriate for that particular class. And so I truly support the moves from the European Union to design this GDPR regulation that basically says that any time an AI system decides something about humans or for humans, then this needs to be explainable, and it needs to be regulated so that it is for the benefit of those people. So that's kind of my high level view of this particular topic. So myself, I am mostly involved in the sort of more technical aspects that are often somewhat further away from the sort of human decision making about humans, and other people who talk about sort of the importance of responsible and explainable AI. They are more talking about these applications of AI that have a more direct societal impact, I would say. Yeah, so to me, of course, I think the biggest barriers are things like security, privacy, and trust. So as we put lots of these AI devices in our homes, right now they start to interact with humans, and the more technology we use, the more vulnerable it also becomes for hacking from outside, from adversarial players, let's say. So how do we keep everything secure and safe? How do we make sure that the data that is being collected or potentially being collected by these devices is not shared with parties that we don't want to share our data with, so that all these things are private by design, that we can truly trust that our data stays in our own sort of safe, and not moves to the cloud to somebody else's sort of system, and sort of how do we certify things like this, right? So when these devices become increasingly more complex, and potentially even self-learning, how are you going to certify something that is changing? And so that we have to, it's already hard to certify things which are highly complex, but we do manage to do this somehow, right? We certify airplanes and and cars, which are already extremely complex pieces of engineering. But if these things become self-learning, that becomes increasingly challenging to do that. And so overcoming that barrier of certifying these things so that we can sort of guarantee that the device is safe and privacy preserving for the people that will use it, and also fair, and all these other dimensions which are important. That's a difficult question. I am for every technology, there's positive and negative applications. It's always the same, and it has always been the same. So if we design an axe, you can use an axe to cut trees and build houses, but you can also use it to kill someone, right? And so this has always been. So personally, I feel a society evolves and becomes more technologically advanced. There's no stopping to it. And we should, as people, we should make sure that we put in the right regulation and laws so that we sort of mostly benefit on the positive side and avoid the negative side. But I'm realistic enough to know that that's not always true. So first of all, it's being done on purpose, which means that people make military weapons from AI. And it seems unstoppable. It seems very hard. It's like it's a weapons race, and it seems very difficult to somehow stop this. Or I don't. It's also not my field so much to understand this. But it doesn't seem that very soon we will be living in utopia in that sense. So I'm realistic, and I'm not always all that optimistic about people and politicians and how they can handle these kinds of questions. I do think there's a lot of really good applications of AI, in particular, for instance, in healthcare, but also many other fields that are worth pursuing it. But in some sense, we built the technology, and we need to make sure and explain to the politicians that how this technology works and what is the potential upside and downside of these technologies. And then we need to involve other people like legal experts, humanities experts, philosophers, politicians, regulators, to make sure that this new technology that is emerging is used for the benefit of humanity rather than against it. And sometimes I feel that too much of that is put at the researcher, right? So they often say, the researcher itself should sort of make these decisions already when they develop the technology. But I think that's somewhat unrealistic in the sense that, it's like asking a mathematician not to work on a fundamental theory of mathematics because in the future, it might be used for bad as well as for good, but it might also be used for bad, right? So I also feel I work on the fundamentals of machine learning, closer to mathematics than to the actual application. And it's when you actually start to work on applications that you're going to make these maybe tough choices. I mean, I never work on military applications. Other people might, but I don't. And so that's where you make these sort of choices, I think. Yeah, so what I find really important, again, and I'm just going to repeat that, is that this is a truly interdisciplinary effort. So we should not leave these questions to the technologists. And I find this very important because we have a very limited view of the world, right? We develop these technologies, but we have a very limited view of what technologies do with our society, or what they do even, with our own sense of security. We will maybe adopt all sorts of technologies, and they might change our psychology, or they might change actually the way we function or the way we think, and that's just very hard to predict. And I think we should really make sure that experts who think about this get involved in order to decide whether certain developments are something that we want to happen. So maybe I can give you one example that sort of has worried me a little bit, which is as we make. So we've seen, for instance, for social media, which we use in our phones every day, that it does change people. And in fact, the things that we read, the things that we get served by social media does actually change the way we think, and maybe even the way we vote. And sort of, I hadn't really thought about that very deeply. I've never worked on this problem, but I could imagine that I could have worked on fundamental technology for this, but maybe in improving a graph neural net somewhere. But I'd never thought about what the impact would be along the line. So I think we need to listen and involve people who do know how these kinds of things will actually impact our lives, and to try to help us a little bit figure out how to sort of make sure that it works in a direction that is good for us. And so here's one example that I worried about a little bit, and I still worry about, which is sort of virtual reality. So it's quite clear that virtual reality, right now we're looking on our phones all day, and I can see kids walking, and they walk and they look at their phone at the same time all the time. So it seems very strange. Now, if we will develop these sort of augmented reality glasses, then we will be connected to internet and to our virtual worlds all the time. And so I think they will be adopted very quickly. And what then, and these systems might get so good in capturing our attention that we will sort of develop some kind of addiction to this, right? So that we want to be in this virtual world all the time. And it may be stronger than ourselves. I mean, if for some, it might already be some, there's clearly the phenomenon of addiction to gaming and things like this. But this only gets worse. And it doesn't feel that we as humans evolve to create better defenses against it, right? So where does that end up at some point in the future? So I think we should so this is one device that, we might have around us and that we might just choose to pick up. But we need to have people think very hard about how to make sure that doesn't go in a direction that's, that will hurt a lot of people, and might even hurt our society, or might hurt our political system or democracy, etc., etc. But again, I want to emphasize that I think it's really important that we involve other disciplines in thinking about that. Well, I think it's not necessarily that they need to be involved at a particular point, but I think they need to be involved now and all the time. They need to be able to monitor what's happening, what the technology can do, and so they need to be also sort of technically intelligent. They need to understand the technology, and they need to think about that and advise about that all the time. But maybe you're thinking about a particular technology, maybe like a self-driving car or something like that. When would you involve people from different disciplines in thinking about sort of the impact of a particular technology? And well, I would think as early as possible, right? As soon as you invest in a technology that that might have a societal impact, you can start to, especially at the regulatory level, you can start thinking about it and involve experts. And the earlier you have regulation around certain technology, the better it is also for the companies that are making that technology, right? So because they know, in which direction to steer the ship, if the technology if the regulation is very clear at that point in time. Okay, so a big theme throughout the last years that has been going on in my lab, in the university lab, but now also at Qualcomm, is something that we call equivariance or symmetries. And so the idea is that the world has certain symmetries, like almost literally like the physical world has symmetries. So for instance, if you take electromagnetism, something looks like an electric field for one observer that's standing still, but then if you move past that electric field, it becomes a magnetic field just because you're an observer which has a different speed. And so this transformation is typically encoded in this kind of what we call covariance or maybe equivariance of the mathematical objects that you're describing. So similarly, for a neural net, you could have that you would transform something about the input. It could be you rotate the input, or you translate the input, or you shear or scale or whatever. Yet you think that the prediction of the neural net should be either invariant, the object identity doesn't change as you rotate the object, but also it could be equivariant, which means if you should do some kind of segmentation, then the segmentation map should sort of transform or rotate, let's say, similarly as you rotate the input. Now, building this kind of idea into neural nets in various ways has been a big theme. We now also do similar things for instance, reinforcement learning. So you can think in reinforcement learning that something that if you're looking at a particular state of the system, and there could be a symmetry that if you take this action in this state, it should be the same as this other action in this other state. And thinking about these kinds of mappings and these symmetries that might exist in reinforcement learning is another theme. We've worked a lot on graph neural networks. So this is if your input space is not sort of an image or sound, one-dimensional signal or two-dimensional signal, but some kind of graph, how would you apply the general ideas of deep learning to these graphs? This is important, for instance, for molecules, studying molecules. So we recently looked at how could you take a molecule, the structure of a molecule as an input, and then map it onto some properties of that particular molecule, like will it cure COVID or something like this, right? Of course, these properties are more subtle than that, but so it becomes like a prediction about what a molecule, how a molecule will act in a body. And then you can combine these things. You can also think about what if I would now add symmetries to this molecule. Clearly, if I rotate a molecule, maybe certain properties remain invariant, maybe others change, and sort of building that into the into the structure of the graph. We've looked at that, and so basically this whole field, thinking about symmetries, thinking about deep learning on manifolds, which I haven't really talked about, like curved manifolds, thinking about graphs, this is called geometric deep learning. So that's been a big theme. And what's interesting about that is that you see that the mathematics that you're using, when you think about that, is very close to the mathematics that you also use in physics. For instance, gauge field theory is a theory about symmetries, in this case local symmetries that you would need if your variables live on a sort of curved manifold. And that theory, as it describes physics, also describes these neural networks, these deep neural networks. And there's a striking resemblance between these two in some sense. Like a deep neural net is just an iterated map. Like you transform things again and again and again. And if you think about an image, this looks a lot like a space. And the space can be curved, and the space can have certain symmetries. And if you go through the neural net, it's like you evolve time forward. And so in some sense, we are building a little mini universe in some sense in this neural net, and you can apply the laws of physics to this kind of mini universe. And so we recently extended these ideas to say, well, what if we are describing sort of a mini universe in the physical sense in a neural net, could we also apply quantum mechanics? What about quantum mechanics? And so this is on my mind right now. I work together with people at Qualcomm on this, but also people at the University of Amsterdam. And sort of the idea is there that quantum mechanics, first of all, if you can implement things on a quantum computer, you could get, a lot more powerful neural networks because, quantum computer is more powerful than a classical computer. That would be one way of looking at it, which is already very interesting. The other way, the flip side of it would be to say, well, is quantum mechanics itself perhaps a language that is different than ordinary probability theory? Because now, instead of having just positive probabilities, which you can only add up, we will now also have negative amplitudes, and positive and negative amplitudes can actually cancel each other out. And this interference is very different dynamics. Could even classically, on a classical computer, sort of designing neural networks with the mathematics or the statistics, if you want, of quantum mechanics, could that already give us a new sort of modeling paradigm? And that is another sort of direction that we are looking into. Okay, so the brain basically has two systems. One is a somewhat unconscious system that you can think of bottom up, where information hits our senses and sort of gets automatically processed through layers of sort of biological neural nets that in our brain, to basically see things in a completely unconscious way or hear things, right? So if I hear you talk, I'm not consciously processing necessary the translation from the sound that hits my ears to the words that I then hear. And similarly, if I look around me, I see objects, but it goes instantaneously and completely unconscious. So that is one type of process. You can think of fast processing. You can think of it as a shortcut. In a way, we have learned to do these things effortlessly. Now there's another process which is much more conscious, and I think that Daniel Kahneman uses type 1 and type 2 thinking or something, fast and slow thinking. So the slow thinking is much more iterative, where you sort of build an argument slowly over time. It's reasoning, and it takes much more effort for humans to do that, and it's also conscious. You have to use your consciousness to basically do this reasoning. It's the kind of process if you try to solve a math puzzle, right? You're really thinking about your building steps, and you're joining sort of reasonings together, you're chaining things together, and that so that's the part that hasn't become conscious. And I think that when we learn, we are putting things, like if you practice something a lot, right? If you practice playing the violin a lot, then some of this conscious effort turns into more and more unconscious effort, and you're starting, instead of the unconscious things now, maybe playing some small little piece becomes much less conscious, but then you can start to focus on the bigger sort of holistic things about a musical piece, and how to put your interpretation on a musical piece like a director would do. So that's sort of these two processes, but so of course when we build neural networks all the way back, they are inspired by how the brain works, and in particular this fast processing, sort of these bottom-up neural nets. But I think more recently we have come to understand that the slow thinking, the reasoning, I mean, there was actually sort of a separate line of research, maybe symbolic AI or logic AI, where this is more this reasoning type of methods, and people have started to think, well, maybe reasoning and causality and sort of symbols and those things are actually can we merge those with the sort of fast processing? So do we have a fast shortcut sort of recognizer, classifier? Can we join that with a sort of more slow reasoning machine? And that's, I think, one of the big questions that the field is facing now. And how do you sort of merge these two things together? Now that's one part of the equation. The one where I believe neuroscience is becoming increasingly relevant is because in one aspect the human brain is a lot more efficient than the hardware that we are building. In fact, it's estimated that the human brain is about 100,000 times more power efficient than hardware for the same task. And so clearly, as our AI tasks, the models become more and more complex, like GPT-3, is a huge model, and so it will also cost a significant amount of energy to execute it, and so you cannot really execute it for every task, because at some point the revenue that you'll get maybe out of your ads is not enough to pay the energy bill. Or if you would run it on a phone, your phone would get way too hot in your pocket, right? So there is ceilings where we basically cannot sort of use the latest and the greatest technology because it's basically too energy hungry. So I think there might become an increasing pressure to get to make these models and make the hardware more energy efficient. And so at Qualcomm we do things like model compression and quantization, so that we run these models on much less precise hardware, like 8-bit integer rather than 32-point floating point precision, that would save a huge amount of energy if you do it that way, right? Now there's still a lot to win, because the brain has a fairly different compute paradigm, and it's far more efficient. And people nowadays think that that's because we're in this von Neumann type of compute paradigm where the memory is separated largely from the registers where the compute happens, right? Where you do the big matrix multiplications and stuff. So you have to move the weights of your neural net, off chip to the places where you do the computation, and you have to do the computation, and you have to move the results all the way back off chip. And this movement is extremely power hungry. So people are starting to think, well, can we design hardware more like a brain? Can we make the memory, for instance, sit very close and distribute it, but close to where the computation happens, so we don't have to move this information back and down all the time? And so that kind of developments, I think, are extremely promising, and they can bring down the power consumption of these networks on a sort of new type of hardware. And then, of course, we haven't even talked about spiking neural nets, but it's unclear yet whether spiking buys you something in the hardware, the silicon hardware that we build, or whether that's something that's mostly useful in the sort of wetware that's in our brain. But these ideas, at least, are very interesting, and we will be looking to the brain in order to make our AI more energy efficient in the future. Yeah, so first, I wasn't necessarily talking about edge computing, because edge computing is sort of a different dimension, which is that some of the computing happens nor on the cloud nor on your device, but sort of more on servers which are on the edge of the compute network, and then your device, I guess your device could also be thought of as the edge. Some of the computation happens at your device and at the smaller edge clouds, and the 5G network would move data back and forth between these things. So that's more like distributed learning or federated learning, if you want. It's a whole different topic. So here I was talking about, any chip that needs to do a computation, whether it's in a phone or whether it's in a cloud or whatever, how can we make that particular chip more power efficient? And so is there an environmental angle? So yes, there is, but I want to say that I am not too confident that if we make our chips more energy efficient, we will be using less power, because I think it's basically we will use as much power as is possible, and as is economically viable. So in other words, if you make things, it's what I call the refrigerator effect. So when I moved from the Netherlands to the US to live there for 15 years, my refrigerator was a lot bigger, but like 4 times bigger or something, and it took a couple of weeks to fill it, right? And then that one was full again all the time. So this is the same with computing. If I give you the same intelligence, but for 4 times less power, you will use all of that. You will use 4 times more intelligence in some sense, because your power is basically the budget. So it still is very useful, but I think we will have to think about this in a different way. We will have different mechanisms to use less power in a way. So for instance, I would believe that we would make sure that the polluter pays, right? In other words, if you use power, you gotta pay for your carbon print, your carbon imprint that you're making by doing that computation. I just think we should really tax pollution and the use of energy a lot more than we're currently doing, because now our future generations are paying for the pollution that we cause, where we should really be paying for it right now. So to come back to your question of, do I think there is an issue with AI using a lot of energy? My answer is yes. As AI is increasing, and becoming increasingly important, it will use an increasing fraction of the available power. As there's a very strong economic driver behind it, it won't just stop by telling companies or people, hey, you're polluting, you should stop that, right? So that's just not going to happen. You should basically tax and put a sort of a climate tax on the use of energy. And I'm a very strong proponent of doing just that. But it is a big issue, the amount of energy that's being used by AI, certainly in the future. So definitely, it's easiest to answer the question in terms of an application I've been working on myself that I'm very excited about. So this has to do with the fact that there are nowadays machines that can radiate tumors at the same time as image the body, right? So with an MRI machine. So this basically means that you get real, a very fast sort of imaging of the body as it moves, let's say as you breathe. And at the same time, there is some kind of radiation beam that sort of destroys the tumor. But of course, as you're breathing, this tumor is moving around, and you want your beam to sort of adapt to that movement. And nowadays, this is not possible. You first make an image, and then you sort of immobilize the patient, hoping that the patient doesn't move at all. But of course, he or she does. And then when you radiate, you often hit healthy tissue, which is very damaging, and you don't hit the cancerous tissue, which means that it's not dead. And so I was very excited about seeing that application. But what it means is that you will have to do far faster MRI reconstruction. So what we need is basically, MRI works as follows. So you basically observe measurements in the frequency, sort of the Fourier domain is what it's called, so basically certain frequencies. And from that, you need to reconstruct the image. And typically, you need, let's say, n of these Fourier moments that you need to measure, but that would take you too long to reconstruct. So now we're going to do with 10 times less of these measurements, so we can get 10 times faster imaging. Yet you still need to be able to reconstruct that image. And so one way to do it is to basically learn from many images that have been reconstructed in the past. Basically look at, okay, with these types of measurements, this is what the image should look like. And this type of measurement, this is what it should look like. So you basically learn to reconstruct a high resolution image. And so there was this particular competition, a fast MRI competition, which was organized by Facebook and NYU. And sort of we participated in that with a technique which are called neural augmentation, where you use a neural net, but you also use a more sort of a classic signal processing technique, and you sort of combine these two together to get the best of both worlds. And so we applied, this kind of technology, and we won in one of the tracks together with a collaboration with Philips. And so, that I thought was a very neat sort of, I would say, application of AI to healthcare. And we are still advancing this further to now also think about which of the measurements do you actually want to do, not just the number and doing well with the small number of these measurements, but actually thinking, okay, which sequence of measurements should I do? So do the first measurement, reconstruct, look at the result, then, okay, what is the next measurement that we need to do, right? And then sort of you sequentially reason your way through, which measurements you should do, which could give another boost in terms of efficiency of these kind of methods. So in healthcare, I think there's enormous opportunity. But of course, there's many other, also in mobility, there's clearly huge opportunity, to build safer cars and, and safer ways to move from A to B. Right now, there's about, 1.2 million deaths per year. And so we should be able to get that down a lot with applying AI technology. Yeah, that's a great question. So I think it's important to think about machine learning as a horizontal technology. And with this, I mean, it is not so much, don't think of it as kind of another application, like autonomous driving or something like, or wireless even, but think of it as a technology that will permeate everything that we do. So all other technologies. And this is what we are currently seeing. Slowly, every field is being basically transformed by AI and machine learning. And so it started from speech recognition and then image recognition and video and all these kinds of things. And then it entered the medical field, medical image analysis. And so it's much more like the internet or a computer or something like that. So there's no way you can avoid it, right? It's like it is a basic technique that will be part of every other application that you will build in the future. And so where will it make big impact? Well, it's a hard question because it will make an impact everywhere, but I can give you a few examples of where I think it's going to make a very interesting impact. So the first one is perhaps in sort of materials design and drug design. So there, I think with machine learning techniques, we will be able to model molecules and the way that molecules interact a lot better with machine learning tools, and we will be able to not only predict which molecules will have the right type of properties that we're looking for, either as a drug or some other material, but we can even sort of specify the properties and then let the system generate the molecules directly. So I can envision a tool where I can say I want a particular material that does this and this and this and this and this, and then the system will turn on and it will just spit out possible molecules that you can test in the lab, and then that have potentially these desired properties. So I can see that's on a very interesting sort of trajectory, that kind of application. Similarly, I could imagine in agriculture where I can see a how would I say it, a self-regulating greenhouse or something like this, right? So in the future, we may not want to use large swaths of sort of field in order to grow our vegetables and other stuff. We want to maybe, like we do in the Netherlands at a very large scale, build greenhouses, or maybe we build huge factories, multi-level factories or something like that, where exactly the right amount of carbon dioxide and exactly the right climate and exactly the right moisture and exactly the right light type that is being used at every phase of a plant growing is being optimized and self-regulated, so that we will grow stuff in these factories at an unprecedented efficiency. I think that might help us sort of feed the world, and it also might be much more independent of the actual environment in which you place these things, right? It could be in the Netherlands, but it could also be in Africa. It's some arbitrary place. You could put these things and you could sort of you run them almost automatically as like a self-driving car, but the software would sort of self-learn and self-adapt. And then within Qualcomm, I think there you can also see a couple of directions where AI is making a profound impact. I would say machine learning. That's, for instance, in wireless communications. Of course, Qualcomm is a company that is all about wireless communication. So up to 5G, I would say many things were hand designed. Engineers basically building on decades of knowledge, they designed these systems, these modems and all these kinds of things by hand. What you see now is that machine learning is going to optimize these kind of systems much further than humans ever could, right? So you generate a huge amount of data. So think about, you want to send data over a noisy channel. Right now, you don't know precisely what the channel looks like, but you can sort of create huge data sets of data in and noisy data out, and then you can learn a system that will learn to decode, or what's called demodulate, the signal on the other end of the channel much better than sort of the hand design systems that we currently have. So what you see is the machine learning again as sort of this holistic technology will help and replace the traditional signal processing tools with these sort of self-learning tools and improve these systems dramatically. And so in the next generations of wireless communication systems, I think machine learning will play a very important role. And then maybe one other one is perhaps chip design. So in chip design, we're also seeing that techniques such as reinforcement learning can sort of, where usually teams of hundreds of engineers would sit together and build these chips together over months and months time. It's a very, very complex process, the engineering process. So what's happening now is that bits and pieces of that process are being taken over by machine learning tools, and eventually it's not hard to predict that machine learning tools will take over the entire process. And since this is such a complex problem, they will do a much better job than these human teams do. Now here it's also interesting that humans will have to work together, of course, with the machine learning algorithms. Certainly in the beginning, they become sort of tools that the humans will use to do a better design, but at some point I think it will be mostly automated, and it will be clear that the automated procedure is actually better than the procedure where the humans do the work, because it's just too complex. So these are just 4 examples, but there's many more. Basically everything you can think of will probably be prone to, at some point in time, to be sort of revolutionized by machine learning in one way or the other. That's my prediction, yeah.